Order of a matrix. Now that we have established a clear understanding that a matrix is composed of horizontal rows and vertical columns, we need a formal way to describe the overall size or dimension of a matrix. In mathematics, this specific measurement is referred to as the order of the matrix. In the upcoming slides, we will explore exactly how to determine this order and the correct way to denote it. Understanding the concept. First, you can think of the order of a matrix as a shorthand way of stating exactly how many rows and columns it contains. Instead of describing the matrix in a long sentence, we use the order to give a quick summary of its size. The reason we do this is that it provides an immediate understanding of the matrix's overall structure. By knowing the order, you can visualize the dimensions of the matrix without having to spend time looking at or counting every individual element inside it. Most importantly, you must remember that the order is always written in a very specific sequence. We always state the number of rows first, and then the number of columns. Please keep this rows first, columns second rule in mind, as it is crucial for the formal notation we are about to discuss in the next slide. Now that we have introduced the concept of the order of a matrix in the previous slide, let's look at what this actually means in practice. Formal notation. Now that we have established the concept of the order of a matrix, let's look at how we express this formally using mathematical notation. If we have a matrix, which we will call matrix A, that consists of m horizontal rows and n vertical columns, we say that the order of the matrix is m by n in terms of notation. We write this as m cross n, however. It is important to note that in a mathematical context, we do not say m times n. Instead, we read this specifically as m by n to ensure there is no confusion. Remember that the first variable, m, always represents the number of rows, while the second variable, n, represents the number of columns. This reinforces the rule we discussed in the previous slide. Rows always come first. For example, if you are looking at a matrix that has 3 rows and 2 columns, you would formally state that its order is 3 by 2. Once you are comfortable with this notation, we can move forward to see how this order allows us to quickly calculate the total number of elements within any given matrix. Calculating the total number of elements. Now that we have established how to denote the order of a matrix as m by n, let us discuss why this information is so valuable. One of the most useful properties of the order is that it allows us to determine exactly how many entries or elements are contained within the matrix without having to count them one by one. Specifically, the total number of elements in a matrix of order m by n is simply the product of m and n. To put this into a formula, the total number of elements equals m multiplied by n. By simply multiplying the number of rows by the number of columns, we can instantly find the total capacity of the matrix. We will see how this works in a practical, real-world scenario in the next slide. Real-world example, inventory management. Now that we have covered the theoretical definition and the formal notation of the order of a matrix, let us apply these concepts to a real-world scenario to see how they work in practice. Imagine you are managing a small stationery shop and you need to track the stock of 2 specific items, notebooks and pens, across 3 different locations: Branch A, Branch B, and Branch C. In step 1, we begin by organizing this raw data into a standard table. Here, the items are listed vertically and the branches are listed horizontally, allowing us to see exactly how many notebooks and pens are at each location. Moving to step 2, we want to represent this information mathematically. We convert the table into a matrix, which we will call matrix S. To do this, we simply remove the descriptive labels and keep only the numerical values. This leaves us with a structured array of numbers. Now, let us determine the order of matrix S using the rules we discussed in the previous slides. In step 3, we identify the number of rows. By counting the horizontal lines, we see there is 1 row for notebooks and 1 row for pens. This gives us a total of 2 rows, so our value for m is equal to 2. In step 4, we determine the number of columns. By counting the vertical lines from left to right, we find there is 1 column for each of the 3 branches. Therefore, our value for n is equal to 3. In step 5, we state the order. Remembering our rule of rows before columns, we express the dimension as m by n. Thus, the order of matrix S is 2 by 3. Finally, in step 6, we can calculate the total number of elements. As we learned earlier, the total number of entries is the product of the rows and columns. By multiplying 2 by 3, we get 6. If we look back at our matrix, we can verify that there are indeed 6 individual pieces of data. While this process is straightforward, it is easy to make small errors. In the next slide, we will discuss some common mistakes to avoid so that you can determine the order of any matrix with confidence. Common mistakes to avoid. Now that we have practiced calculating the order of a matrix using our inventory example, it is important to discuss some common pitfalls to ensure your accuracy. Beginners often make a few specific errors when determining the order of a matrix, and I want to make sure you avoid them. First, let's address the issue of reversing the order. This is the most frequent mistake, writing the number of columns first and the rows second. For instance, a student might mistakenly write 3 by 2 when the correct order is actually 2 by 3. To prevent this, always keep this simple phrase in mind: rows before columns. Next, be careful not to confuse the multiplication sign. In the notation m by n, the cross symbol is used as a shorthand to describe the dimensions of the matrix. It is not necessarily a command to perform a multiplication calculation immediately, although, as we discussed in the previous slide, the product of these 2 numbers does indeed give us the total number of elements. Finally, there is the issue of miscounting. When you are dealing with larger matrices, it is quite easy to lose track of the count. A helpful tip here is to physically point to each row from top to bottom and then each column from left to right to ensure your count is perfectly accurate. Once you have these precautions in mind, you will be well prepared for our final summary of the topic. Key takeaways. First, remember that the order of a matrix is simply the formal way we describe its dimensions, or in other words, its overall size. As we have emphasized throughout the session, this order is always expressed as rows times columns. Please keep this sequence in mind to avoid the common mistake of reversing the 2. In mathematical terms, if you encounter a matrix with m rows and n columns, we formally refer to it as an m by n matrix. Finally, as we demonstrated in our inventory management example, you can quickly determine the total number of elements within a matrix by multiplying the number of rows by the number of columns, which is calculated as m times n. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of the concept.